Hey there, so today we're going to tackle two pretty important questions in chemistry. How do we get a really accurate pH reading? And what in the world is this powerful technique called titration? Trust me, understanding this stuff isn't just for chemists in a lab, it's key for everything from medicine to making sure our environment is healthy. So let's just dive right in. Have you ever really stopped to think about why a lemon has that super sharp, sour taste? Or, on the flip side, why getting even a tiny bit of soap in your mouth is so bitter and just plain awful? It's something we all know, but the science behind it is actually really cool and, believe it or not, pretty simple. Well, the answer to both of those questions, and honestly to a ton of things in the world around us, all comes down to one simple little number. And that number is the pH. It's like a secret code that tells us exactly what's going on chemically inside a substance. All right, so let's get right to it. Our first topic, what exactly is this pH scale anyway? The easiest way to think about the pH scale is to imagine it's a kind of ruler for chemists. It runs from 0 all the way up to 14, and pretty much any substance that has water in it can be placed somewhere on this ruler. Where it lands tells us if it's acidic, basic, or sitting right there in the middle. And here's how it all breaks down. Anything with a pH below 7 is considered acidic. Yep, that's our lemon juice. A perfect 7 is neutral, which is where you'll find pure water. And anything above a 7 is basic, or what some people call alkaline. And that's exactly where our soap from earlier fits in. See? Simple. Okay, for those of you who like the math behind it all, here's the formula. Now, I know it might look a little intimidating, but the main idea is actually really straightforward. That H+ just stands for hydrogen ions. These tiny particles are what make something acidic. The key thing to remember is that it's an inverse relationship. So the more hydrogen ions you have packed in, the lower the pH number goes and the more acidic it gets. So we get what pH is. That's great. But the next logical question is, how do you actually measure it? Let's take a look at how it's done. Turns out we've got a few different tools for the job. You've got your simple pH paper that just changes color. Then there's the super precise digital pH meter. But for what we're talking about today, we're going to focus on that third one, chemical indicators, because these guys are the secret to understanding our next big topic. And this is a perfect example of how an indicator works. Meet phenolphthalein. I like to think of it as a chemical spy. When it's in an acidic solution, it's totally colorless, just hiding out. But the second that solution turns basic, bam, it reveals itself by turning this really bright pink. That color change is the signal we're going to be looking for. Knowing the pH is one thing, but what if you have a solution and you have absolutely no idea what its concentration is? How do you figure that out? To solve puzzles like that, chemists use a very precise and clever technique. And that brings us to chemical titration. At its heart, titration is basically a detective method. You've got this mystery solution with an unknown strength. To crack the case, you carefully add a different solution, one where you know the concentration exactly until you hit a perfect balance point between the two. The entire goal here is to reach what we call neutralization. You want to add just enough of your known chemical to perfectly cancel out the mystery one. Not a drop too little and not a drop too much. So how do we know when we've hit that sweet spot? Well, that's where our little color-changing spy comes back into play. All right, time to put on our virtual lab coats. We're going to walk through a classic titration experiment, step by step. You ready? So here's our setup. We have a burette. That's the long glass tube that lets us add a liquid with incredible precision, like 1 drop at a time. The flask is where we'll put our mystery solution. In this case, our unknown is an acid, and the tool we'll use to measure it is a base. And, of course, we need our indicator to tell us when to stop. Okay, here we go. The process is very careful. First, we measure out a very specific amount of our unknown acid and put it in the flask. Next, we add a couple drops of our indicator. See? Still totally clear. Now for the crucial part. We start adding the base from the burette, super slowly, swirling the flask, just watching, waiting for that one single drop that's going to change everything. And This is it. This is the endpoint, the exact moment the solution turns pink and stays pink. That one single dramatic color change tells us we have now perfectly neutralized every last bit of the acid in that flask. We've done it. We have all the information we need. So what do we do with that information? We plug it into this beautifully simple equation. M1V1 equals M2V2. Here, M stands for molarity, which is just concentration, and V is for volume. The thing is, we know 3 out of these 4 values. So now it's super easy to solve for the one thing we didn't know, the original concentration of our acid. It's just so elegant and powerful. And this whole thing brings us to a really important idea, one that this phrase sums up perfectly. Chemistry is not difficult if you understand it the right way. By breaking a process like titration down, what seems like a really complex procedure becomes this logical, step-by-step story. Which really makes you wonder, what other complex things out there are just waiting to be understood in the right way?